So my topic for today is radar-based approach to in-vehicle occupant sensing. So we know that radars have been used on the external vehicle environment, and I would like to also try to understand how radars can be used in vehicles. So I'm based at the National Transport Design Center in Coventry, where we focus on human-centric research. So the solutions that we develop is all the more relevant with the advancement of autonomous vehicles and shared mobility. So we work in a multidisciplinary approach, supporting research from different fields and coming up with collective solutions. So jumping right into the topic, we know that the automotive industry today has already shifted towards conditional automation, which brings safety, which makes it as a major priority. And talking about safety features, we know that vehicle safety is categorized into two, active safety features and passive. Active safety features try to prevent accidents, whereas passive safety features work to minimize the damage, prioritizing occupants and their well-being. So the diagram here is just an example of what in-vehicle occupant sensing actually means. So it inclines towards passive safety systems, prioritizing occupant safety. So we have features such as seat occupancy, vital sign monitoring, occupant movement, occupancy detection, and pet safety. As observed, most of the features are camera-based in today's world. Although it is a very efficient solution in terms of cost and simplicity, we do not have the same kind of methods when it comes to physiological features such as vital sign monitoring. We still rely on contact-based biometric sensors such as ECG and respiratory bands, which might not be a good solution in real-world scenarios. In the same way, I think the question that we need to ask is there another approach which not only detects occupants but also brings in the physiological component to it? The answer is yes. We can use short-range radars in vehicle cabins for this purpose. So short-range radars emit short wavelength radio electromagnetic waves, which are reflected by the objects that are present in their path. Some of the examples are millimeter wave radar and frequency modulated continuous wave radars, which we call as FMCW radars. So the important aspect here is that these reflected EM waves will give us information about where the target is present, at what angle, and the velocity at which they're moving in case they're in motion. And this can happen even in short range. So this is the basic working of FMCW radars, where they emit signals that are called as chirps because of the linearly increase in frequency. So the transmitted chirp gets reflected by various objects, which can be a mixture of static and dynamic objects and humans as well. And the reflected chirps are received at the receiver. So we need to make meaning of this. So the transmitted and the received chirps are mixed to make something called as a beat signal, which is the most important component here. So beat signal will give us information about, just as mentioned before, the range, angular information, and the velocity at which it moves. So why this is important for physiology is because FMCW radars are very sensitive to phase changes. So although we can detect humans that are present in front of the radar, it can detect small movements even in their, such as chest cavity movements due to respiration and heart rate, and this can be detected by FMCW radars. These are some of the advantages of FMCW radars when compared to other methods that we have today. So the first one is that it protects privacy, maintains anonymity, which is a given. Second one is we have good resolution, and to be honest, it can be up to millimeter range in certain modules. The third advantage is it's immune to temperature differences, unlike certain sensors that we have today. The fourth advantage is it's able to measure target distance and velocity at the same time. So the fifth one is the most important advantage when we think of it in a physiology point of view. This is a non-intrusive technology where we do not need to mount sensors on occupants to understand the physiological activity. And the sixth advantage is that it has the ability to penetrate through materials, so it works well even in occluded situations. And although, last but not the least, although it is a short-range radar, it offers good range up to 20 meters. So this is one of our research output at the NTDC. We use a FMCW radar mounted on the A pillar of the car. So it's a two-stage process where the first stage, you can see the flow chart of the algorithm. So the first stage is just pre-processing, where we try to understand the time domain signals of these FMCW signals. And we try to generate heat maps to understand seat occupancy. So it's a very simple case scenario where, as you can see in the end, the first heat map has no occupancy. The second heat map does indicate a signal intensity which is close to the radar that we can understand that there is driver seat occupancy. And the last but not the least, we try to detect whether the rear passenger is present or not. And this, again, we can understand with the high intensity in the radar arena. So it's a simple scenario, and these heat maps are fed into the neural network where we're using convolution neural networks to train and classify these images. So from this, we can understand that not only can we detect humans, we can also detect their positions by further improving the algorithm. So the second output that we have is we're trying to understand physiological properties of occupants. So we try to process FMCW radars to understand the phase angle variation of their chest. So as I mentioned earlier, the slightest movements in the chest cavity can be detected by FMCW radars, such as the rising and falling, detecting heart rate and breathing rate. So the phase angle variation, along with validation data that is from the ECG that we've collected, is fed into a neural network. Here we're using recurrent neural networks because we are dealing with time series data. We've tried to reconstruct ECG signals. As you can see, the output does not look anything like ECG, I know, but we are able to detect the R peaks of the ECG signal, which is more than sufficient to understand average heart rate and to derive heart rate variability features from it. So this can be further used to understand driver state monitoring or just for vital sign monitoring purposes for passengers and occupants. So in conclusion, so radar-based in-vehicle sensing does overcome disadvantages that are posed by camera or other sensor methods when it comes to convenience and privacy. Although there are some challenges with radars, of course, motion artifacts is one of the most important challenge that can be overcome by using machine learning or deep learning algorithms. In the same way, signal complexity also can be reduced by employing deep learning techniques. So keeping this in mind, we have a few use cases that can be used with occupant detection and physiological monitoring. So we know that electric vehicles and futuristic autonomous vehicles will depend, their performance will depend on the occupancy. So it can be used for that. It can be used for occupancy-based warning system, anti-theft alerts, and lastly, for vital sign detection and driver monitoring systems in takeover situations. So having that said, I would like to conclude this presentation by saying human-centered research is also important for future mobility and to make that a success. Thank you.